Yeah. So, hello everyone. So, for today's last talk, we have Vikram Voleti. Uh, he is a PhD student at Mila University of Montreal, Canada, supervised by Professor Christopher Pal. Yeah. Also,
So,
hello everyone. So, for today's last talk, we have Vikram Voleti. He is also visiting researcher at University of Guelph with Professor Graham Taylor. His current research interests broadly involve generative modeling of images and videos. He has worked as a research intern at Google as well, where he worked on active speaker detection in videos. He has prior research experience at IIIT Hyderabad, India, in video synthesis and lip reading. He has also worked as a consultant on semantic segmentation for autonomous driving and as an engineer at an autonomous robotic company. Today, he's going to talk about GANs. So, Vikram, I guess you can start.
yeah, thanks, Heath. Hi, everyone. My name is Vikram, as Heath introduced. I'm a PhD student at Mila. Mila, in case you didn't know, is the research lab headed by Joshua Bengio. We are located in Montreal, Canada. Um, the topic for today for me is GANs, the story so far. So GANs have been pretty much dealt with quite extensively in the past few years since their introduction. So I'd like to go through a brief history of GAN architectures and how they evolved over time. What were the motivations behind that evolution? As well as talk about a few tricks of the trade and some misdemeanors. So how can you possibly misuse it? How can you possibly go wrong with using it? That's it. So to begin, so GANs are generative adversarial networks. I'm going to split up the three words, and I'll say first of all, so generative. My research is mostly on generative models. So this is generative versus discriminative. Discriminative modeling is when you have, let's say, an input distribution and an output distribution, and you'd like to discriminate your input distribution to get your output distribution. For example, if you have images and the images belong to certain classes, you'd like to discriminate among the images so as to get the class of the images. So what happens in that process is you end up classifying your input data by discriminating against different, let's say, features or different areas of the input probability distribution. Generative modeling, on the other hand, models the probability distribution itself. So that way, once you have a framework for modeling the data itself, from that framework, you can infer a lot of things. For example, if you were to model the data distribution of images as a conglomeration of, let's say, different Gaussians belonging to different classes, by inferring those Gaussians and the weights of those Gaussians for a particular image, you can infer the class of the image. So that's a very broad overview of how generative modeling works versus discriminative modeling. So in brief, you model the generative distribution of the image in the sense that you try to generate the image or whatever data you're dealing with. And by generating it, you make a model for that generation. And from there, you infer a lot of good qualities or good features. Networks, because, well, we're in the era of neural networks again. So a lot of the innovation in deep learning and in neural networks has happened thanks to good hardware improvements over the past decade. And so it's important to understand that one of the reasons why neural networks are back on track is that the hardware is able to support them now. And finally, adversarial, because there are two adversaries in this model. That one's a generator and one is a discriminator, typically called generator and discriminator, and they're competing against each other for some goal or for some supervised loss. Um, so to be brief about it, I'm sure you've seen this or a similar diagram in other places. So I'm going to briefly talk about how it works. So the goal is to be able to generate images, let's say, or any sort of data for that matter. GANs have been popularized for the image generation in the past few years and video generation as well, but they can be used for any sort of generation, any sort of data generation. All you're doing is modeling a data distribution. But in our example, we'll look at images. So here's a real image. This is an image that I want to generate. Don't want to generate just this image. I want to generate a whole bunch of images, including dogs, let's say. So this particular image has been lifted from the ImageNet dataset. It's the image of a golden retriever, as you can probably see. And so I would like to model the whole space of golden retriever images so that I can generate a new golden retriever image. So what I do for that is I first say I can make a model of that distribution of golden retriever images as a Gaussian distribution. When I do that, so a Gaussian distribution is you have, let's say, the real number line, and you can sample various values like -100, +200.3476, whatever. You can sample all of them. It just so happens that when you keep sampling from it, you will get more numbers in the area of the mean and lesser numbers away from the mean. Why we use a Gaussian in general is because usually real world phenomena follow Gaussian distributions, typically. So I say that if I can sample a set of numbers from the real number line that follow a Gaussian distribution, I can map them into an image deterministically, let's say. So the only stochastic sampling that's being here is for the noise, which is Z. Oh, let me switch on my pointer. Yeah, that is Z. So I'm sampling a noise value, and I'm deterministically mapping that to an image. Obviously, this image does not look like a dog or anything for that matter. So I would like to train this generator such that when I sample a noise, I get an image. How do I do that? One of the ways that I can do that is, okay, I sample a noise, I map it to an image, and I say, hey, this image is supposed to be this image. So I take a loss between them and then backpropagate through the generator and train the generator such that it satisfies that MSE loss, or it minimizes that MSE loss. The problem with that is I am enforcing a mapping from the noise to the image. I'm saying that this particular noise has to map to this particular image. I'd like to do something better than that. So what I do instead is I give it a very sparse signal. I'll just say your image is wrong or your image is correct, as in your image is real or your image is false, and that's it. There's no other information pixel wise or semantic information wise and so on and so forth. In order to do that, I have a second network called a discriminator. As the generator is being trained, this discriminator is also being trained to check whether an image is real or not. So the way the discriminator is being trained is it's being shown real images and saying, this is a real image, please train yourself. And I'm showing images from the generator and saying, this is actually a fake image, so train yourself to identify this fake image. So what the discriminator is trying to do is it's trying to say this d of x is real and d of g of z is fake. Now, in order for the generator to generate real images, it needs to bias the discriminator such that the output of d of g of z is real. So then we can say that the generator's output is a real image or close to a real image. So whereas the discriminator is trying to lower this, if you understand that d of g of z is 0 means it's false and 1 means it's true. So the discriminator is trying to make this 0, but the generator is trying to make this 1. So in a nutshell, the discriminator is trying to minimize something and the generator is trying to maximize something. Take a negative of that, take a log of that. So the discriminator is trying to maximize something and the generator is trying to minimize something. So this is called a minimax game in game theory. Usually the equilibrium point is called a Nash equilibrium. There's a lot of theory behind that as well. I'm not going to go into that too much right now, but suffice it to say that when you have a noise, you pass it through a generator so that you get G of Z. You pass it through the discriminator and the discriminator aims to make this 0. So it tries to maximize 1 minus of that value. So you have a max on the discriminator weights, and it's trying to maximize this. It's also trying to maximize d of x. So we want d of x to be 1 or as high as possible, because x is definitely real. And you take an expectation in the sense that you showed a bunch of noise or a bunch of images and you average across them. So on an average, the discriminator needs to say that all these images are fake, and on an average, the discriminator needs to say that all these images are real. And the other way around for the generator. The generator on an average needs to be able to make the discriminator say all these images are real. So the first GAN paper appeared in about 2014, and they had pretty good samples on MNIST, on faces, on CFAR10, and on another data set in the wild. So they were able to show that this can actually work pretty well. Not that adversarial models didn't exist before, they did. It's just that the innovation here was that we used neural networks, and they work pretty well in the case of images, and we had the right hardware to support them. GANs were a paper from Mila. Ian Goodfellow was a PhD student at Mila back then, so this was during his PhD that he made that he innovated on GANs, and he got a couple of papers on GANs and a tutorial on GANs and so on and so forth. So once this paper got out, it seemed pretty innovative, and a lot of people try to innovate further in that. One of the usual ways in machine learning to incorporate some information is that you would like to condition your network in some way, or condition your model in some way. Conditioning is you don't just blindly map from, let's say, an x to a y or an x to a z or whatever. You condition it, giving some additional information. So you don't just say, here's an image, figure out where the location of the object is. You might also give it some additional information saying there is a bird in it, something like that. Some conditional information is conditioned to that particular image. So there's conditional information that's being incorporated. Similarly for GANs, what they did was, in the generator, they gave a conditional information of the class. So the conditional information here is the class. So I'm giving you a noise vector. Generator, please give me an image, conditioned on the fact that it should belong to class, let's say, 1. Discriminator, here's an image, either from the generator or from the real data set. And please make sure that this image belongs to this class. So that way the generator gets information from whether the discriminator is able to say the image generated belongs to that particular class or not. And that way it's able to map, how do I use my class information to generate an image. So as you can see, for this row, the class information was that the digit is a 0 in MNIST. So you have various various images that are generated that are zeros, and so on and so forth for the rest of the classes. So this is a way where they conditioned the GAN. Shortly after that, there was another GAN paper called DCGAN. By the way, I'm not exhaustively covering all GAN papers. I'm only trying to cover very few of them. There are many GAN papers that deserve our attention, but I'm not able to cover them in interest of time, and I'm only covering those which have helped me in my own research. So then came DCGAN. It essentially replaced all fully connected layers and all pooling layers with convolutional layers. It replaced FC layers with convolutional layers, and it took care of pooling by increasing the stride. And it generated images using a strided transpose convolution, I think. So it generated pretty good images as well. And then it also showed that you can perform vector arithmetic on it. So if you remember from NLP, there was this model that you could say king minus man plus woman equals queen. Those sort of vector arithmetic that you can do in the latent space. So they were able to show that you can do that. You can say that there are vectors that correspond to man with glasses. There are vectors that correspond to man without glasses, that is noise vectors. And there are noise vectors that correspond to women without glasses. If you manipulate these noise vectors and then you generate an image, you can actually get some good semantic information from them, which is woman with glasses. So you're performing an arithmetic operation there. Uh, so DCGAN got really popular, especially because they've replaced all FC layers with convolutional layers, and now you can really use your GPUs to perform really fast training. And most GAN architectures now build off from this as well. So you'll hardly find any GAN architectures, especially in images, that use any FC layers. Another paper that got really popular and I personally loved was InfoGAN. So it's an information maximization approach. So what it says is your latent noise that you have from which you're generating an image, we would like to have a lot more information packed in there. We would like to morph it or warp it such that we can pack some disentangleable information in there, so that at generation time I don't have to wonder what would I get from this noise vector. Instead, I can look at the noise vector and guess that the kind of image that I'll get is like this, and manipulate it such that I get a certain kind of image. For example, once I train this, I can identify different dimensions in the noise vector that, let's say, correspond to the azimuth, the pose, or the elevation, or the lighting in the scene. And when it comes to MNIST characters, let's say, so I can, so there is one noise vector that corresponds to the class. There's one noise vector that doesn't really have a clear meaning, but there's one noise vector that corresponds to the rotation, so inclination, let's say, and there's one noise vector that corresponds to thickness of the character. So you're able to do this because they argued. So let's say you have a noise vector Z, and then you have a conditioning variable C. It's all the more trivial for the generator to just ignore the class condition. How do you ensure that it takes cognizance of the fact that it has a class condition and needs to condition on that? The way they approached it is you maximize the mutual information between the image that's generated and that conditioning variable that you're giving. Here, the conditioning variable is not class. Again, the conditioning variable is another random noise vector, discrete and continuous. But you're increasing the mutual information between the image and the class. In simple words, mutual information, think of it as some sort of an information content that belongs to both. So what you're trying to do is your image should give you some information about your class and your condition, and your condition should give you some information about your image. That way, they're able to uh, disentangle the condition vector in such intuitive ways, and they're able to show some good results. Then around the same time, there were two papers that came out called ALI and BigGAN, that is adversarially learned inference from our lab, Mila, and bidirectional GAN. What they argued is, in order to link the generated image and the noise vector better, just give them both to the discriminator and say that, hey, discriminator, check if this noise vector and this image belong together. Now, you can't do that for real images because real images don't really have a noise vector. So now, instead of a generator, you also have an encoder. So you go from real image to noise as well as noise to image. So noise to image was your generator. Your real image to some fake noise is your encoder. So now you take your image, you map it to noise, and give that real image and fake noise to the discriminator. And that is one side, either real or fake, depending on how you choose to see it. And then you have pure noise, real noise, and you have a fake image. Give these two as a pair to the discriminator and let the discriminator figure out which side it belongs to. And let each encoder or generator fool the discriminator in not being able to see the difference. Same concept here as well. So there's a generator that generates from noise to image. There's an encoder that encodes from image to noise. You give both to the discriminator. Both of these were published at ICA 2017. So this was one effective way of, again, linking the noise to the image. Then there was a paper that improved on class conditional information with a very simple idea. What they said is, okay, so the discriminator receives the generated image. The generator anyway receives noise and a class condition, let's say. The discriminator receives this image and the class condition. But apart from an adversarial loss, it also has a classification loss. That means when the discriminator sees the image, it should be able to say this image belongs to this class. It should be able to classify the image. So there's a classifier network there. And so the generator needs to generate an image such that the classification network works. And this is one of the first papers that attempted 128 by 128 size images. Earlier, all the images were like 32 by 32 or 64 by 64 max. This is the first one that tried, one of the first ones that tried ImageNet 128 by 128. And it got pretty good results there. Then came another paper called StyleGAN. So by this time, people had figured out that training GANs is pretty difficult. When you train GANs, you don't really have a good signal to tell you if training is happening apart from just checking the images themselves visually, manually. There might be some tricks there, but they're only tricks. So how do you A, stabilize the training of GANs, and B, visualize if the GAN is improving on its training or not? So what they said is the original GAN formulation has the loss function such that it translates to minimizing the Jensen-Shannon divergence between the data distribution and the fake distribution, the generated distribution. This necessarily implies that there's not a lot of correlation between the loss and the quality of the mapping. And they were able to show some simple examples where the Jensen-Shannon divergence does not indicate whether the distributions are close together or not. Or rather, they came up with a better metric called the Wasserstein distance. I'm sorry, they didn't come up with Wasserstein distance. They said that the Wasserstein distance can be used as a better metric to measure if the data distribution and the generated distribution are close together or far apart. And so they use the Wasserstein distance as the loss function and as the actual metric, and they derived a loss function from there. And they were able to show that if you check the Wasserstein distance across training iterations, you can clearly see that there's an indication of whether the images are very bad or whether the images are close to the real distribution or not. And they were able to generate good images by then. And by then, we had already come up with inception score for the training of GANs to check the quality of images. So inception score came around that time, I think. Then there was another paper called Wasserstein GAN with gradient penalty, WGAN GP, which said, yes, Wasserstein GAN is correct. It's a better metric, but it uses weight clipping. So instead of weight clipping, what we would like to do is to use a gradient penalty. So the concept is, in order to stabilize the training of GANs, the insight is that the discriminators' neural network functions need to be constrained in their functional form. So if there is a delta change in the input, there shouldn't be a very high change in the output. If there's a very high change in the output compared to the input, that means it's unstable. The discriminator is going to go haywire. So you need to constrain that change. This translates to what is called the Lipschitz constant. So Lipschitz constant is that ratio of change in output by change in input of a function. So they said we would like to constrain this in some way. WGAN did that by clipping the weights. So it said that if the weights are not beyond a certain range, it's constraining that Lipschitz constant in some way. But we'd like to do it in a better way. So what we do is we have a constraint on the gradient. We have a penalty on the gradient itself. So whatever output the discriminator has, that output's gradient with respect to the input is an estimate of the Lipschitz constant. So we would like to constrain that itself directly. And so they included that term in their loss function, their loss function being built from WGAN. And so they were able to show that whereas DCGAN and other GANs, including WGAN, gave okay results, we gave better results. And by the way, so WGAN's loss value and WGAN GP's loss framework is pretty much what a lot of GAN architectures used after that. So as you can see, the community was evolving to to a place where they really wanted to stabilize the training of GANs in a theoretical way and get to good, stable training regimes, because they already figured out that hyperparameters play a big role in the training of GANs. One of the earliest GANs that showed really good results on images was progressive GAN. So what they said is they had a very simple idea. They said we will first generate images in very low resolution, that is 4 by 4, let's say. So we will train a generator and a discriminator such that it generates very good 4 by 4 images. And then we'll add layers to the generator and the discriminator, and we'll try to generate 8 by 8 images, building off of this frozen 4 by 4, frozen or fine-tunable 4 by 4 weights. And slowly we'll keep adding weights, adding layers to the generator and discriminator. And eventually they showed they were able to bump up to 1024 by 1024 quality images, so HQ level images. And so this gave very good results, and GAN started getting noticed by a lot of people at a lot of places. That, yeah, I mean, it's not that GANs are very hard to train and so on. If you train them correctly, you can actually get really good results on them. So continuing the story on stabilization of GANs, there was a paper called Spectral Normalization GAN that came up around that time in 2017, 2018-ish. What it said is, so yes, the name of the game is to constrain the Lipschitz constant of the discriminator. We choose to do that. So WGAN did that by weight clipping. WGAN GP did that by getting a penalty on the gradient. We will do that by dividing the weight with its largest eigenvalue. This is called spectral normalization. So a spectrogram is, let's say, the series of eigenvalues, the decomposition into eigenvalues. And so spectral normalization is you make the maximum eigenvalue of that weight matrix 1. How do you do that? You divide it by that maximum eigenvalue. So that's what they did. How it works for FCs is more or less okay, but how it works for convolution networks is not that obvious. So they came up with a way to do that. And what they did was they didn't get the exact estimate of the eigenvalue, maximum eigenvalue, but they got a rough estimate of it. And throughout training, they only took this rough estimate. So the method is called power iteration method, where you estimate the eigenvalue based on an iterative method. So you get to one iteration, you get to one estimate. The next iteration, you get a better estimate, and so on and so forth. They used only one iteration. And they said this worked pretty well. They have a lot of graphs to show how it works. They did a lot of hyperparameter tuning. And they showed that for different hyperparameter settings, WGAN GP fails in many hyperparameter settings. Weight norm is more or less okay, but it's sort of not that great. Spectral norm ensures diversity and so on and so forth. So they were able to show that this is one good way and fast way of ensuring that you have stable training of GANs. And then came the paper that blew up the space in GANs called BigGAN by DeepMind. So it had state-of-the-art results on conditional high-res image generation from ImageNet. So previously the inception score was 166, was 52, and it bumped up to 166 on 128 by 128 images. Inception score is one image quality metric. FID is another image quality metric. FID is a distance, so you minimize that. So previously it was 18, held by self-attention GAN. They were able to decrease it to 9.6. And inception score is, you bump it up, the bigger is better. And so they bumped it up from 52 to 166. And these were state-of-the-art results back then. The key takeaway from this was that they bumped up the batch size from, let's say, 256 to 1024. And that was the main insight as to how they were able to get to such great quality. How were they able to handle such huge batch sizes? They used Google TPUs back then. So not really reproducible by everyone, but yeah, they got great results. They released the pre-trained model and so on and so forth. So I'll go through some of the insights of BigGAN. First of all, it builds on top of self-attention GAN. So self-attention GAN was a GAN that came up just before this. And the insight of self-attention GAN is that in your generator, have one layer that's a self-attention module. You might be aware of attention modules from NLP and from transformers. So transformers are essentially one variant of attention modules. Self-attention is that your query and your key and your value are all the same thing. They're all the same vector or the same tensor. And so you take one tensor, you try to figure out what is important in it. You take that importance mask and you map that mask onto that input and you take out the important features. So that's your attention map, which gives you what is relatively more important than something else. And you multiply that with your input and or a modification of your input, and you get some good features out of your previous features. So this was one layer in self-attention GAN, and they were able to get to really good image quality metrics. BigGAN built on top of this. What it did was, one of the things was it used conditional batch norm. So self-attention GAN used just batch norm. It was perhaps unconditional, I forget. BigGAN used conditional batch norm. So this is an image that I borrowed from the paper film from Mila. So essentially, it's conditional batch norm. What it says is, you might be familiar with batch norm. When you have a feature, you find out the mean and standard deviation of that feature across your batch, and you normalize that. That is, you using those mean and standard deviation values, you make the feature have a zero mean and unit standard deviation, and then you renormalize it so that it has some mean and standard deviation that suits your purpose. So here you have batch norm, and then you renormalize that batch norm. To renormalize it, you take the help of your class condition. So you're supposed to renormalize your features based on the class that you're supposed to produce. And this is how they have one single generator module that can produce different classes. So it's the same module, you just condition it on different classes, and you will be able to get images of different classes given the same noise vector. Typically the same domain as conditional GANs, except that the conditioning is in the conditional batch norm instead of concatenation of the input or a product of the input and so on and so forth. The other change that they made was they used hinge loss. So again, hinge loss was used by self-attention GAN. It was used by other GAN architectures as well. I'm just using this opportunity to tell you what that is. So the GAN loss is the discriminator tries to make the output of a real image 1 and the fake image 0. Hinge loss says, yeah, that's too much of a constraint. Instead, I'm okay if the discriminator gives me any value greater than 1 if it's real, and I'm okay if the discriminator gives me any value less than 0 if it's fake. If for a fake image it gives me a value above 0, that's wrong. Punish the discriminator for that. If the discriminator gives me any value less than 1 for a real image, that's wrong. Punish it for that. But for a real image, if it's any value above 1, there's no punishment. So this sort of moves away from the usual domain where you have some particular loss function for every output. Here, you don't have a loss function for every output. If your discriminator is good on some output, that's great. You don't change the discriminator. You don't even tell it that you're right. It's okay. So that's hinge loss. There are other innovations that they made. They use TPUs and so on and so forth. Then the more important innovations were, and this is table 1 in their paper. So what they show is, well, the self-attention GAN baseline is on a batch size of 256. We bump it up to 2048. Sorry, not even 1024. It's 2048. That is when we get really good improvements on the FID and inception score and speed up in the iterations. Speed up because you're using TPUs and so on. You also increase the width of your channels. So if your channels had 64, you make it 128 and so on and so forth in every layer of the generator discriminator. And that also gave you a big improvement in the FID and in the inception score. Mostly the inception score was on top by then itself. All the rest of the changes was in a Reddit post. I think Andrew Brock, the first author of this paper, said, "Yeah, we were about done by then." All the rest of it was only to write a paper on it. So they had shared embeddings with linear projection, like I said. So linear projections from your class conditioned embeddings, and the embeddings were shared among all layers. So typically what you do is you have your condition, you embed it for a layer and you give it to that layer. You embed it for another layer and give it to that layer. To save on memory, they had the same embedding and they give that same embedding to all layers. So this improved memory, so this drastically improved the speed. Um, and then they had a hierarchical latent space. So this is another interesting innovation that they did. Again, hierarchical latent spaces are not new. They've been in practice in many other models. It just so happens that they used it for GANs. So what they said is, your noise vector, I don't want to generate an image from one noise vector just as it is. Instead, I will split the noise vectors into different portions. The first portion corresponding to low level features, the second portion corresponding to certain high level features, the third portion higher level features. And so at every upsampling, I introduce new features. And so because there's a hierarchy in your noise vector, it's called a hierarchical latent space. And that got more improvements in their FID and assumption score and so on. They also had something called orthogonal regularization. I'm not going to go into that, but that also gave them good improvements. It's important to know that in case you've not read the BigGAN paper, or even if you have read it, make sure you go through the appendix, because the appendix contains a lot of information on what went wrong with their training, what are all the different modules that they tried, how the inception score and FID changed with training, and so on and so forth. So it's really good info to keep in mind, especially if you're dealing with GANs. One of the other things that I'd like to show you is something called latent interpolations. In machine learning, there's this concept of overfitting, where if you have a model, there's not a lot of guarantee that says that the model is memorizing on your inputs and outputs. So for example, if you have images and their classes, if your model maps from images to classes, there's a very high chance that the model is actually just memorizing, that is, it's learning by heart, that this image maps to this class, that this image maps to this class. And it's not actually figuring out what is in that image, what is it that makes this image belong to that class, and so on and so forth. So one of the ways to counter this is, especially in GANs and in generative models, is because you're mapping from a latent space, which is noise, to images, if you're able to show that when two latent points map to two images, all the latent points in between also map to realistic images, then your model is not really learning something by heart, it's actually learning some relevant information. So that's what they did, and they weren't the first ones to do this, by the way. So all the papers that I've talked about before have also done this. So they were able to show that, okay, if one noise vector leads to, let's say, this dog image, and one noise vector leads to this this bird image, then all the latent points in between, you do a linear interpolation between those latent points, and you generate images from them. They also more or less correspond to some in-between variant of these two. And so that's what happens with any two points. They also show results on what if you fix a certain range of values in your noise vector and only change the rest. And then they were able to show that for some values of your noise, you're preserving the pose. So for example, if a dog is looking this way, it transitions from a dog into a bird looking that way. So they were able to show that it is in fact learning some relevant information. These particular noise dimensions learn to pose information, and so on and so forth. So different noise dimensions learn different informations, and so it's not learning anything by heart, it's actually learning something in the latent space. And then on Twitter, there was this GIF that was produced of a random walk in the latent space, where they started with a dog, and then they just randomly walked in the latent space and generated and decoded all those latent points into images and showed the transition among the images. I would also like to point out that there are some weird examples here. So not everything is rosy. You have some very weird examples where your noise vector doesn't really map to a realistic looking image. For example, this is supposed to be a lion, I think, and this is supposed to be an ape, I think. But obviously, they don't look anything like realistic lions or apes. So everything is not rosy. You have to know that a giant part of AI in general and GANs especially is hype. So you can't just take a GAN or take a machine learning model for that matter and think it will work for every case. You need to know the nuances of how it works and where it won't work and how do you mitigate that. I'm going to come back to this point towards the end of the presentation again. I'm going to skip this, so this describes different normalization techniques. If you want to know more about this, you can go through the group norm paper. It gives a very good summary of them. Instead, I'm going to tell you about StyleGAN. So StyleGAN was another big GAN paper that got very popular for generating realistic faces. None of these faces are real, so back then it was huge news. The way they did this is, so this is your entire generator, and they split up the generator into two parts, a style network and a synthesis network. So what the style network does is it maps the noise to a style vector, so what they call a style vector. What the style vector does is it's a representation of the various styles. So for example, hair color, shirt color, age, gender, and so on and so forth. So the style vector is supposed to represent those. And then you have a synthesis network, which uses something called adaptive instance norm. You can look at that in normalization techniques. And so it was able to leverage the style vector to produce a certain kind of image. And they were able to show that retaining the content, so this noise corresponds to the content and this noise corresponds to the style. So retaining the content but changing the style, you can produce different kinds of images, so different kinds of faces and so on. We're going to move away from pure image and go to image translation. And one of the earlier works in this is called pix to pix. So it's a paired image to image translation technique. And what it says is if you have, let's say, one kind of images and you would like to map them to another kind of images, you can have a discriminator on both. So input and the generated, and real and the input. And so your discriminator is able to say whether they're real or fake. And so your generator will train such that it can map between one kind of image and another kind of image. So for example, the realistic satellite map to Google Maps kind of map, or an outline of a building onto an actual building, and so on and so forth. A better version of this was unpaired image to image translation. So you actually don't have paired images here. You just have a bunch of images of one class and a bunch of images of another domain, sorry, not class, and you're able to train this such that it maps between the two domains. And they show some really cool results on it. And they first of all showed that it works in the pix to pix area as well. And then they showed how it works in loads of other areas where it works on style transfer. If you give an image, you can generate an image as if it was generated by Van Gogh, because one of the domains is your input image domain and the other domain they fixed to all Van Gogh paintings, and so on and so forth. And they showed how you can blur images or blur the backgrounds of images using the same technique, and so on and so forth. So StyleGAN really bumped up the level at which GANs can be played with. Another GAN architecture that sort of leveled it up even more was called GAN right now, or it was called SPADE. So what it said is when you're doing normalization, you just take the entire feature, you find out the mean and variance, and you subtract and divide that, and then you renormalize it. What if I do this per pixel? I don't normalize for the entire feature, I only normalize per pixel. And so given an input image and a conditional image, so for example, this conditional image, or given this noise, so this conditional image, you extract features from it, and you renormalize a noise such that it generates an image conditioned on these per pixel. And so you're able to do these cool things where per pixel you have certain information, some certain local information that you're able to preserve. Another paper that did image to image translation is called StyleGAN. What they said was, why are you limiting yourself to just two domains? You need to bump it up to multiple domains. You should be able to go from one domain to another domain to another to another to another using the same generator. The way they do this is they condition the generator on the target domain. So you give an input image, you give a target domain. That target domain could be one of multiple. And so you train your GAN that way. And so they're able to show that given an input image, you can map it to different domains such as angry and happy and fearful. So it's the same content, but different domains of, in this case, emotion. Another paper that came out from a PhD student who's currently a PhD student at our lab is called relativistic GANs. What she said was the original GAN formulation says the discriminator is trying to see whether an image is real or not. But a better formulation of that is the discriminator should only be able to tell whether one image is more realistic than the other image. That is a better way of training a generator. And so she has a difference of the output of the discriminator for a real image and the output of the discriminator for a fake image, and she optimizes over that difference, and she shows that you're able to get better images and so on. And then there's this one GAN architecture that incorporated 3D information. What it says is, in the middle, I will get to a representation of the 3D scene in its entirety, and I will manipulate it in 3D and then generate an image. So what I do with that is I have injected geometric information into the model. So now at test time, I can choose the 3D angle at which to look at the scene, and I can generate the same scene from multiple angles. So you see that we're going more and more towards how do you incorporate interpretability? How do you incorporate certain geometric biases? So this whole field is called geometric deep learning, by the way. So how do you make them more interpretable? How do you make them more explainable, and so on and so forth? And then I think lastly, so there's this paper called Vid to Vid that sort of bumped it up and said, okay, we're going to do this for videos. So what they do is, it's the same thing as pix to pix almost. They're mapping from a semantic segmentation map to real images, and not just images, to frames. And so they're able to propagate that information across frames in a multi-scaled way. So you see that you can amp up GANs a lot more to various applications. I'm going to skip this one. One of the more ethical uses of GANs is to visualize climate change. So this uses cycle GANs, as we've seen before. We map from a real image to what it would look like if it were to be a victim of flood. So this is a paper from Mila which said that we would like to visualize the effect of climate change. In order to get people to realize what's going to happen, you take real photos of real houses of real people, and you show them how it would look like in a flood. And you show them that this is what's going to happen, so you need to act now. So this is one of the more ethical and moral uses of GANs in general. And so there's a lot of talk on the ethics behind GANs and how do you use GANs in an ethical way and so on. There was a recent controversy on Twitter about that as well. So it's important to know that any domain in machine learning in general is subject to these ethics and biases, and people are more and more moving to a place where they're able to use these models ethically while leveraging all of the improvements that have happened over time. So I'm going to pause here and I'm going to take some questions because I think we have about 10 minutes left. I'm happy to stay a little longer, but I'm happy to take some questions.
Yeah. So it is great hearing, and the GANs are fascinating to hear about every time. So yeah, we have a lot of questions right now. So the first question is, how do we find the Gaussian distribution for a multidimensional data set, like a data set that has a lot of features in it?
Mm-hmm. When you say how do you find the Gaussian distribution, correct me if or I don't know. So the way I understand the question is, so you have a multi-dimensional data set, and you're trying to fit a multi-dimensional Gaussian distribution over that
Gaussian.
data set. So there are many ways of doing that, not necessarily related to GANs. So there's something called Gaussian mixture model that you can use.
Yeah.
But it's important to understand that all these are approximations. In real world scenario, when you have a multidimensional data set, all you're doing is saying, I think there are multiple Gaussians that can explain this, or I think there is even one Gaussian distribution that explains this. It's what I think. I may be wrong, but assuming that there is a Gaussian distribution that explains this, I will try to find out the parameters of that Gaussian distribution. And so you assume some parameters, initial parameters, and you try to see how that Gaussian distribution fits your data, and you'll calculate how much it doesn't fit your data, and you optimize for your Gaussian parameters. In a nutshell, that's how it works. There are many improvements on this. There is expectation maximization. There are different ways of doing that. But in a nutshell, that's how I've seen people usually do it.
Yeah, so Gaussian mixture models and all. So
Correct.
yeah. So the next question is, have GANs been used in reinforcement learning, for example? Any interesting papers, results, or applications of GANs in this reinforcement learning field?
Right. So to my knowledge, I'm not sure of a paper that got popularized for using GANs for reinforcement learning. The problem with GANs is that you're making a generative model of your data. Why do and a lot of reinforcement learning depends on synthetic data, discounting the section of reinforcement learning that deals with natural images and deals with real world scenarios. So when you have an environment that can generate exact data for you, why do you need a GAN? Why do you need to make a generative model of that? Is one question that I have. So perhaps using GANs in that perspective may not be ideal, but sure, you can use GAN to generate new scenes. You can use GANs to generate new levels. There was recently a GAN from, I think, NVIDIA Toronto or Uber Toronto, I forget, which is able to generate new game levels.
Yeah,
So
I
it's
read that
really
paper.
good.
It generated a Pac-Man game, the whole game engine and all.
Correct, exactly. So they had a differentiable render and so on and so forth.
Yeah.
So maybe GANs can be used for that. But I'm right now not aware of any popular papers that use GANs very effectively in reinforcement learning. I can get back to you on that.
Yeah. So one question that I had was, GANs have these generative generators and discriminators as two different networks, and I didn't find any works that used pre-trained like discriminator networks, because we know that GANs are hard to train in nature, and like replacing one discriminator with a pre-trained discriminator or a pre-trained network will be even more hard to get to that Nash equilibrium that we have in GANs. So any insights on how like we can approach this sort of problem?
Sure. So first of all, saying that there is a Nash equilibrium that is reached and stuff is, I mean, it's correct, but it may not translate to any good intuition on how do you train your model now, because you're dealing with such a high dimensional space that you don't really know where the equilibrium is.
Yeah,
All you can say is, okay, maybe you've reached a saddle point, or maybe you've reached a mode collapse point.
let's approach
Right.
towards a minimum.
So um, so your question is, how do you train GANs in a stable way? Well, your first part of your question is, why do you not use a pre-trained discriminator? So this has been slightly addressed in the earlier papers of GAN as well, including WGAN and including DCGAN and so on. The problem, or the actual framework, is that your discriminator is learning simultaneously with your generator. Suppose you have a discriminator that is pre-trained, so it knows exactly how a real image looks like and it knows how a fake image looks like. So then when the generator gives the discriminator a fake image, because generator is not trained yet, the discriminator will be immediately able to say this is fake. And what happens with that is, at some point your gradients will get saturated, and so all the time all you're saying is this is fake, this is fake, this is fake. And so it's very difficult to let your generator learn, because all it knows is it's always wrong. It doesn't know when it's right.
Yeah.
So that's why you don't use a pre-trained discriminator. Instead, you train your discriminator along with your generator. So when the generator reaches a certain level where it's able to generate some realistic images and some non-realistic images, your discriminator is also at the same level where it's able to say, okay, these images are real, but these images are fake, but nothing more than that. And so if the generator overpowers your discriminator, that's also bad. If your discriminator overpowers your generator, that's also bad. So if you've trained GANs and if you've seen places like, for example, mode collapse and places like
Yeah.
your image is just too bright, that's when the discriminator overpowers your generator
Yeah.
in typical cases. So that's why you
So
don't use
that
that.
I guess answers one more question. Like,
Hmm?
can you discuss some of the good practices to avoid mistakes, these mistakes that are there? So
Right.
another question
So if
is,
I were to elaborate on that, yeah. So one of the best methods that I've personally used is to actually observe the output of the discriminator. So I check d of x and d of g of z and see how those values change with respect to time. If I see that d of x is pretty much above 1 or close to 1 and d of g of z is constantly varying, then I know that the discriminator is overtrained. The
yeah.
discriminator is not at all doubting any real image. So that's how I get back and change my hyperparameters and so on. So that's one advice that I can give.
One more question is, what are the current limitations that GANs face, and what could be the major direction in this sort of GANs approach that can be there?
Right. So a lot of GAN research is going on in how do you, let's say, use self-supervised training? How do you make, so essentially the target is that you make a generative model of your data. The problem is that your data itself may be biased, your models themselves may be biased to prefer a certain kind of data rather than other data. Another side to this is what are the potential unethical applications of it. For example, if you use a super resolution GAN, you can super resolve from a very hazy image to a really good image of a face. It could be used to identify missing people, let's say, but it could also be used to identify and target certain groups of people for unethical purposes. So there are the both sides of the coin. So the point is to identify how do you nail the ethics of it and how do you nail the biases in your algorithms and your data set and your model and so on. So that's one good direction in which GANs are being used. Another direction in which GANs are being used in is in few shot settings. For example, biomedical images, you have very, very few and very, very sparse, and not a lot of biomedical labs collaborate with each other. So each of them have their own small subset of data. So you can use GANs to train on these small subset of images to be able to generate more images of the same domain. The problem again is, what if your GAN is wrong? What if it's stupid? What if it generates an image of that is supposed to be a benign image, but it's actually the image of a malignant brain scan?
Yeah.
So that's something to take care of when you're doing this. So in the biomedical image domain, a lot of people are doing that. How do you negate this bias? How do you make sure? How can you train such for in a few shot learning, but uh, uh, compensate for the biases?
Yeah. So there are two questions that are very similar sort of questions. So are there any good approaches that generalize GANs to discrete labels like generating words, basically in text, how you use GANs, which is very different from what images are.
Hmm. Right. Um, Two directions in this. Um, with respect to images, there is something called text to image and image to captions. So you give an image and you generate a caption out of it. And there are these GANs called stack GANs V2, stack GANs plus plus, I think, and so on and so forth. So there's a thread of GAN architectures there which go from, let's say, an image to a caption or a caption to an image. Um, GANs are also used on audio data. So when you
Yeah.
say discrete data, you mentioned text, but actually any data, any digital data is discrete.
Yeah, even using
You can
this.
model it using continuous distributions. But yeah, so using GANs for audio has not received a lot of success. Um, Not sure why. Using GANs for text generation also has not received a lot of success, perhaps precisely because it's difficult to make a generative model of your text given such a sparse signal as yes or no. So we've seen the explosion of transformer architectures, but we haven't seen GANs in the text domain. So maybe that's something to pursue, but maybe people have pursued it and seen that it doesn't work very well.
Yeah, like I have seen some basic approaches that are made in even music pieces. Like one
Right.
very popular paper was MuseGAN, which worked pretty well that I know of basically.
Yeah,
Yeah.
yeah. So music GAN was one. I think it was GANsynth. GANsynth was one that worked pretty well, but that was after like 3 years of research on it by Google Brain Magenta. So
So yeah, any one more question is, are there any approaches explicitly incorporating temporal information, which you talked about, like audio pieces or anything like most GAN works are on images, like so time series video seem to be a harder work than just static images. So can you elaborate on that?
right. So in the recent architectures that are out there, I can talk about video first. So there's one. So there's Vitavid that I showed you. So it's a multi-scale architecture in the sense that you have a final resolution and you have a half resolution, half of that, and so on. And at each scale, you have a discriminator. And so the discriminator not only tries to see if the image is correct or not, it tries to see that by your input being the images in the last few frames, last few time steps, and the output being the image at the next time step. So conditioned on your previous time step, whether your current frame looks correct or not.
Yeah.
So bit to bit does that in one way. There's DVD GAN, one of the more complex and more hardware heavy architectures, which essentially splits up the problem of video generation into two parts, spatial and temporal. So you have you have a generator that generates frames, but you have two discriminators. One discriminator looks at whether the new frame looks spatially correct, and the other discriminator looks whether the sequence of frames looks like it belongs to a real video in time. So this is called DVD GAN. So it has two discriminators. Um, GANs have not really been used in time series modeling very famously, very popularly. They may be used, but I think that you have better, more intuitive ways of modeling time series than using GANs. The real power of GANs is in higher dimensions. In lower dimensions, you can check how the GAN works and you can see whether it really models them correctly or not. I think that it's in lower dimensions, it's just better to go for more reliable, more stable architectures than GANs. But yeah, in time series, in especially in videos, there's a lot of work on using GANs.
Yeah, so for the last question that we have, can you discuss some direct real life applications of GANs, not indirectly like augmentations or improving model robustness, but some direct application that we can use it out of the box?
Use it out of the box. Apart from applications like image to image translation, you mean?
Yeah, I mean, the question itself has like where we can directly use like when we have face recognition systems, we can directly use it in a security sort of a camera where it detects the image or
Right.
not.
So I guess the question is not indirectly in augmentation, improving model robustness, etc., but some direct application. So I guess a lot of the GAN architectures that I showed you have direct applications where you have given, let's say, semantic segmentation maps of a video of a self-driving car, use the GAN to generate the image in the future so that you know what's there in the future, where they are, and so on, and how do they look. Use a GAN for style transfer. So there's a field of deep learning called neural style transfer,
Yeah,
where you use a neural network to transfer the style from one kind of image or one kind of data to another kind of data. People have used this to transfer the style of an author as well in text. So
yeah,
GANs could be used for that. You can use GANs, for example, for an ethical use case, such as the one that I'm showing you right now, visualizing climate change, where you use a cycle GAN and you've trained it on a certain input domain and a certain output domain, and you can easily use it for transferring from one domain to another, especially if the second domain has very few classes, provided that you took care of them. So a lot of the applications that I've said are related to image translation. Apart from this, it also has all the usual use cases and applications of generative models, where once you have a generative model, now you can make inferences on that generative model. Given a data distribution, you can check how the manifold of that data is being modeled by the GAN and what the consequences of that are. Maybe you can do auto distribution detection and so on and so forth. All the usual consequences of generative modeling that also happen.
Yeah. So I guess that wraps up the questions and this session. Like it was a very informative session, and thank you for being a part of this event that we have planned.
Great. Thank you for having me with. I hope I was able to contribute something to your
Yeah, it
symposium
was
and
a great
people learned something today. And thank you for having me.
yeah.
Hello everyone. So we'll be again starting with our second session tomorrow morning at 11 a.m. and see you all tomorrow. Thank you for staying with us throughout the day today, and hope you all enjoyed it.